Good evening, and welcome back to the Nocturnal Astronomer. I'm your host, Atlas Reed, and tonight we're going to explore one of the most recognizable patterns in the entire night sky, Orion the Hunter. This magnificent constellation dominates our winter evenings, a celestial signpost that has guided travelers, inspired poets, and captured human imagination for thousands of years. We'll journey through the mythology that gave Orion his name, examine the remarkable stars that form his body, discover the stellar nurseries hidden within his sword, and understand why this particular grouping of stars appears so brilliant during January nights. We'll talk about distances that challenge comprehension, temperatures that would vaporize any known material in an instant, and cosmic processes that are creating new stars even as we speak. If you enjoy these types of videos, I'd appreciate it if you'd give this one a thumbs up and subscribe to the channel. It really helps me continue making these astronomical journeys for you. I'm also curious, where are you watching from tonight, and what time is it where you are? Drop a comment below. I always enjoy hearing from fellow skywatchers around the world. Let's dive in. When you step outside on a clear January evening and look toward the south, assuming you're in the northern hemisphere, you cannot miss Orion. Even if you've never studied astronomy, even if you cannot name a single constellation, you've probably noticed this striking pattern. Three bright stars aligned in a nearly perfect row form what we call Orion's belt, and they're surrounded by four additional brilliant stars that mark his shoulders and feet. This configuration is so distinctive, so immediately apparent, that cultures across every inhabited continent have created stories about it. Orion rides highest in the sky during January, which makes this the perfect time to become acquainted with him. The constellation rises in the east during early evening hours and climbs to its highest point around midnight. Unlike some constellations that require a dark sky and considerable imagination to perceive, Orion shines through light pollution, through thin clouds, through the bright glow of a nearly full moon. He's visible from virtually everywhere on Earth, from northern Alaska to the southern tip of Chile, from Tokyo to Nairobi to Sydney. The ancient Greeks saw in this star pattern a mighty hunter, the son of Poseidon, god of the sea. According to their mythology, Orion was a giant of extraordinary strength and beauty, a hunter so skilled that he boasted he could kill any animal on Earth. Different versions of his story offer different endings. In one telling, the goddess Artemis fell in love with him, but her brother Apollo disapproved of the relationship. Apollo tricked Artemis into shooting Orion with an arrow, and in her grief, she placed him among the stars. In another version, Orion's boasting angered the Earth goddess Gaia, who sent a scorpion to kill him. The gods placed both the hunter and the scorpion in the heavens, but on opposite sides of the sky so they would never meet again. You'll notice that as Scorpius rises in the east during summer months, Orion sets in the west, as if fleeing from his ancient enemy. But Greek mythology represents only one culture's interpretation. The ancient Egyptians associated these stars with Osiris, their god of the afterlife and resurrection. The three belt stars aligned, perhaps not coincidentally, with the three great pyramids of Giza. The Babylonians saw a shepherd or a true king. Hindu mythology identified the constellation with Prajapati, a deity associated with creation. Indigenous peoples of North America had numerous interpretations. Some saw a canoe, others a group of dancing warriors, still others the cosmic footprint of a great spirit. What's remarkable is that despite these vastly different cultural interpretations, nearly every civilization that looked up at this group of stars saw something significant, something worthy of their greatest myths and stories. This speaks to the constellation's visual power, its undeniable presence in our sky. Now let's examine the stars themselves, starting with the most obvious feature, the three stars of Orion's belt. From left to right as you face south in the northern hemisphere, these stars are named Alnitak, Alnilam, and Mintaka. Their names come from Arabic, reflecting the medieval Islamic astronomers who preserved and expanded upon ancient Greek astronomical knowledge during Europe's Middle Ages. Alnitak means the girdle, Alnilam means a belt of pearls, and Mintaka means the belt. These three stars appear to lie in a straight line, and they're remarkably evenly spaced from our perspective. But this alignment is an illusion of perspective, a cosmic coincidence. In reality, these stars are nowhere near each other. Alnitak lies approximately 815 light-years from Earth. Alnilam is about 1,340 light-years distant. Mintaka sits roughly 900 light-years away. Imagine three birds flying at different altitudes, separated by hundreds of feet, but from your position on the ground they appear to be flying in perfect formation. That's what we're seeing when we look at Orion's belt. Each of these belt stars is a blue supergiant, a type of star that burns incredibly hot and bright. These are not stars like our Sun. Our Sun is a yellow dwarf star, modest in size and temperature, burning its hydrogen fuel at a steady, sustainable rate that will keep it shining for approximately 10 billion years total. The stars of Orion's belt are profligate spenders of their nuclear fuel, burning through their hydrogen at rates that would make our Sun seem almost frozen in comparison. Think of it this way: if our Sun is a person carefully managing a retirement account, making modest withdrawals that will last a lifetime, the stars of Orion's belt are lottery winners throwing extravagant parties every single night. They're spectacular, brilliant, impossible to ignore, but they'll burn through their resources relatively quickly. Alnilam, the middle belt star, shines with the brightness of approximately 375,000 suns. Try to grasp that number. If you could somehow gather 375,000 stars exactly like our Sun and combine all their light, that's how much energy Alnilam pours into space every second. This tremendous energy output comes from the star's size and temperature. Alnilam has a surface temperature of about 27,000 degrees Kelvin, compared to our Sun's relatively cool 5,780 degrees. At these temperatures, the star glows bright blue-white. The star itself is enormous, with a radius approximately 40 times larger than our Sun. If you placed Alnilam where our Sun sits, its surface would extend past the orbit of Mercury and nearly reach Venus. But here's the cost of all that magnificence. Alnilam is only about 4 million years old, practically an infant by astronomical standards, and it's already used up most of its hydrogen fuel. Within another few million years, this supergiant will exhaust its nuclear reserves and explode as a supernova, briefly outshining every other star in our galaxy combined. From Earth, located over 1,000 light-years away, we would see a new star appear in Orion's belt, bright enough to be visible during daylight, casting shadows at night. It would be one of the most spectacular astronomical events in human history. Beyond the belt, Orion's body is marked by 4 additional bright stars. The upper left shoulder, as you face south, is Betelgeuse, whose name comes from Arabic and roughly translates to the hand of the giant or possibly the armpit of the giant, depending on which linguistic interpretation you prefer. Betelgeuse is one of the most famous stars in astronomy, partly because of its remarkable characteristics and partly because its name tends to make people smile. Betelgeuse is a red supergiant, and it represents a different stage of stellar development than the blue supergiants of the belt. If the belt stars are young adults in the prime of life, burning bright and fast, Betelgeuse is approaching the end of its journey. This star has already exhausted the hydrogen in its core and has moved on to fusing heavier elements. As it does so, the star has swollen to truly staggering proportions. The exact size of Betelgeuse is difficult to measure because the star's outer layers are not well defined. The surface is turbulent, with huge convection cells carrying heat from the interior to the exterior, causing the star's radius to vary over time. But astronomers generally agree that if you placed Betelgeuse at the center of our solar system, its surface would extend past the orbit of Mars and possibly reach Jupiter. That's a sphere large enough to contain millions of stars the size of our Sun. Despite its enormous size, Betelgeuse is cooler than our Sun's surface, with a temperature of only about 3,500 degrees Kelvin. This relatively low temperature gives the star its distinctive reddish-orange color. Hot things glow blue, cooler things glow red, and this principle applies whether we're talking about a flame, a heating element, or a star. Betelgeuse's red glow is the color of a dying giant. And dying it is. Sometime in the next 100,000 years, possibly tomorrow, possibly not for many human generations, Betelgeuse will explode as a supernova. When it does, it will briefly become as bright as the full moon, visible even in daylight, and it will remain visible for weeks or months before fading. It will be a spectacular event, and it will pose no danger to Earth. The star lies about 548 light-years away, far enough that the radiation and particles from the explosion will have dispersed to harmless levels by the time they reach us. Now let's look at Orion's other shoulder, the upper right star as you face south. This is Bellatrix, a name meaning female warrior in Latin. Bellatrix is a blue giant star, hotter and more massive than our Sun, but not as extreme as the belt stars. It lies approximately 250 light-years from Earth and shines with the power of about 9,500 suns. Moving down to Orion's feet, we find two more bright stars. The lower left foot is Saiph, whose name comes from Arabic meaning sword of the giant. This is another blue supergiant, though less luminous than the belt stars, lying about 650 light-years away. The lower right foot is Rigel, whose name means the foot in Arabic, and this star is truly extraordinary. Rigel is the brightest star in Orion and the seventh brightest star in Earth's entire night sky. Like the belt stars, Rigel is a blue supergiant, but it's even more powerful. This star shines with the light of approximately 120,000 suns. At a distance of about 863 light-years, Rigel appears slightly brighter than Betelgeuse despite being much farther away, simply because it produces so much more energy. The star's surface temperature reaches about 12,000 degrees Kelvin, giving it a brilliant blue-white color that contrasts beautifully with Betelgeuse's ruddy glow. Hanging from Orion's belt is a line of fainter stars that form what we call Orion's sword. This vertical line extends downward from the belt, and it contains one of the most magnificent sights in the entire sky, the Orion Nebula, also known as Messier 42 or M42. To the unaided eye, the middle star of the sword appears slightly fuzzy, as if you're looking at it through an unfocused camera lens. This fuzziness is not a defect in your vision. You're looking at a vast cloud of gas and dust, a stellar nursery where new stars are being born right now. The Orion Nebula is one of the very few nebulae bright enough and close enough to be visible without optical aid, and it's certainly the most spectacular such nebula visible from mid-northern latitudes. Through binoculars, the nebula reveals itself as a gray-green cloud surrounding several bright stars. Through a telescope, especially one with a large aperture, the nebula becomes almost overwhelming in its structure and detail. You can see dark lanes of dust, bright regions where young stars are illuminating the surrounding gas, and intricate shapes that have earned various nicknames: the fish mouth, the wings, the fan. The Orion Nebula lies approximately 1,344 light-years from Earth, making it one of the closest regions of active star formation to our solar system. The nebula spans about 24 light-years across, though the dense star-forming region at its heart is much smaller, only about 4 light-years in diameter. To give you a sense of scale, 1 light-year is the distance light travels in a year, moving at 186,000 miles per second. That's about 6 trillion miles, or 9.5 trillion kilometers. So when we say the nebula is 24 light-years across, we're talking about a cloud so vast that light, the fastest thing in the universe, takes 24 years to cross from one side to the other. If you could somehow travel from one edge of the nebula to the other at the speed of a commercial jet, about 500 miles per hour, the journey would take approximately 30 million years. This immense cloud consists primarily of hydrogen gas, with smaller amounts of helium and trace quantities of heavier elements. The gas is incredibly thin by Earth standards. The densest regions contain about 10,000 hydrogen atoms per cubic centimeter. That might sound like a lot, but Earth's atmosphere at sea level contains about 25 quintillion molecules per cubic centimeter. By our standards, the Orion Nebula is a near-perfect vacuum. Yet there's so much total material, spread across such an enormous volume, that the nebula contains enough gas to make approximately 2,000 stars the mass of our Sun. At the heart of the nebula lies a group of 4 bright young stars called the trapezium, named for their trapezoidal arrangement. These stars formed recently, probably within the last million years, and they're extraordinarily hot and bright. The most massive star in the trapezium, known as Theta 1 Orionis C, is a blue giant with a surface temperature of about 45,000 degrees Kelvin and a luminosity approximately 200,000 times that of our Sun. These hot young stars are sculpting the nebula around them. Their intense ultraviolet radiation heats the surrounding gas, causing it to glow. This is why the nebula shines. It's not generating its own light through nuclear fusion the way stars do. Instead, it's fluorescent, like a neon sign. The ultraviolet light from the trapezium stars excites the hydrogen atoms in the nebula, giving them extra energy. When those atoms relax back to their normal state, they emit visible light, primarily in a wavelength we perceive as greenish. Let's spend some time understanding how stars form, using the Orion Nebula as our example. Star formation is one of the fundamental processes in the universe, and it's happening right now in that fuzzy patch of Orion's sword. The process begins with a cloud of gas and dust, like the Orion Nebula, drifting through space. These clouds can remain stable for millions of years, with the gas pressure pushing outward balanced by gravity pulling inward. But something can disturb this balance. Perhaps a nearby supernova explosion sends a shockwave through the cloud. Perhaps the cloud collides with another cloud. Perhaps the cloud simply grows large enough that its own gravity becomes irresistible. Once the cloud begins collapsing, gravity takes over. Imagine a vast, diffuse cloud slowly contracting, like a parachute folding in on itself, but in 3 dimensions and on a scale of trillions of miles. As the cloud collapses, it heats up. This might seem counterintuitive at first. How does something get hotter by collapsing? Think about pumping up a bicycle tire. As you force air into a smaller volume, the tire gets warm. The same principle applies here. Compressing a gas heats it up. As regions within the cloud collapse, they form dense knots called protostars. These are not yet true stars because they're not generating energy through nuclear fusion, but they're on their way. The protostar continues to gather material from the surrounding cloud, growing more massive and more dense. The core temperature rises. 1 million degrees, 5 million degrees, 10 million degrees. At around 10 million degrees Kelvin, something extraordinary happens. The hydrogen nuclei in the core are moving so fast, with so much energy, that when they collide, they overcome the electrical repulsion that normally keeps atomic nuclei apart. They fuse together, forming helium and releasing tremendous amounts of energy. A star is born. In the core of a star like our Sun, 620 million metric tons of hydrogen fuse into helium every single second. That might sound like an alarming rate of consumption, but the Sun contains enough hydrogen to maintain this rate for about 10 billion years total. It's been fusing hydrogen for about 4.6 billion years so far, and it has about 5 billion years to go before it exhausts its supply. The energy released by fusion in the core travels outward, eventually reaching the surface and radiating into space as light and heat. This outward pressure from the energy production exactly balances the inward pull of gravity, and the star reaches a stable state that can last for billions of years. This balance is called hydrostatic equilibrium, and it's what keeps stars from either collapsing under their own gravity or exploding outward from their energy production. In the Orion Nebula right now, we can see this process at various stages. There are protostars still gathering material, hidden deep within dark clouds of dust. There are young stars that have just ignited fusion, still surrounded by disks of leftover material that might someday form planets. There are slightly older stars that have cleared away their birth clouds and are settling into a long, stable adulthood. Astronomers have used infrared telescopes to peer through the dust and identify more than 700 young stars within the Orion Nebula region. Many of these stars are surrounded by protoplanetary disks, flat structures of gas and dust rotating around the young star. These disks are where planets form. Within these disks, dust grains stick together through static electricity and gentle collisions, gradually building up into pebbles, then boulders, then planetesimals, and eventually into full planets. Our own solar system formed this way 4.6 billion years ago, in a nebula much like the Orion Nebula. The Sun and all the planets, including Earth, condensed from a rotating disk of gas and dust. When you look at the Orion Nebula, you are seeing the process that created our world, happening again, happening right now. 1,344 years in the past from our perspective because the light has taken that long to reach us. Not all nebulae glow. Near Orion, particularly in the region south of the belt and around the nebula, you will notice dark patches where fewer stars are visible. These are not holes in space. They're dark nebulae, clouds of dust so dense that they block the light from stars behind them. The most famous of these is the Horsehead Nebula, a dark protrusion that resembles a horse's head and neck silhouetted against a brighter background. The horsehead is actually part of a much larger dark cloud, and it's only visible because it happens to lie in front of a glowing emission nebula. The Horsehead Nebula is one of the most photographed features in the sky, though it's challenging to see visually even through large telescopes because it requires precisely the right combination of aperture, magnification, and contrast. These dark nebulae are cold, typically around 10 to 20 degrees Kelvin, only slightly warmer than the coldest temperature theoretically possible. At these frigid temperatures, gases freeze onto dust grains, forming ices of water, ammonia, methane, carbon dioxide, and more intricate organic molecules. These are called molecular clouds because the conditions allow atoms to bond into molecules, which would be torn apart in warmer environments by ultraviolet radiation. Molecular clouds are the coldest, densest places in interstellar space, and they're where star formation begins. The Orion molecular cloud, which includes the Orion Nebula and the Horsehead Nebula, is one of the closest such regions to Earth and one of the most studied. This cloud contains hundreds of thousands of solar masses of material, enough to form a significant population of stars. When astronomers study these clouds using radio telescopes, they can detect the faint radio emissions from molecules like carbon monoxide. Carbon monoxide is useful because it's common in these clouds and it emits radio waves at specific frequencies that can penetrate the dust. By mapping the carbon monoxide emission, astronomers can trace the structure of molecular clouds, revealing the dense cores where stars will form. What's fascinating is that these dark, cold nebulae are not empty voids but active chemical laboratories. Despite the near absolute zero temperatures and the incredibly low density, molecules are constantly forming, breaking apart, and recombining on the surfaces of dust grains. Astronomers have detected over 200 different molecules in molecular clouds, ranging from simple two-atom molecules like hydrogen gas and carbon monoxide to complex organic molecules with dozens of atoms. These include formaldehyde, ethanol, the same alcohol found in beverages, glycine, an amino acid, and even sugar molecules. The presence of these organic molecules in space has profound implications for the origin of life. When stars and planets form from these molecular clouds, they incorporate these pre-existing organic molecules. When our solar system formed 4.6 billion years ago, it inherited a chemical inventory from its parent molecular cloud. Some of those molecules eventually found their way to Earth, perhaps delivered by comets and asteroids, providing some of the raw materials for life. Let's zoom out now and consider where Orion fits into the larger structure of our galaxy, the Milky Way. Our galaxy is a spiral galaxy, shaped like a disk with spiral arms curving out from a central bulge. If you could view the Milky Way from above, it would look somewhat like a pinwheel or a hurricane system, with bright spiral arms tracing out from the center. Our Sun sits about 26,000 light years from the galactic center, roughly halfway out from the center to the edge, in a minor spiral arm called the Orion Spur or Orion Arm. Despite its name, this structure is not the constellation Orion, but rather a small spiral arm named after the constellation because many of the bright stars in that direction lie within this arm. When we look at the constellation Orion, we're looking roughly perpendicular to the plane of the galaxy, outward from our local neighborhood into a region populated by relatively nearby stars. The stars of Orion, lying between about 400 and 1,500 light years away, are all part of what astronomers call the Orion OB Association, a loose group of young, massive stars that formed from the same giant molecular cloud and are now slowly drifting apart. An OB association is a group of O-type and B-type stars. These are the hottest, brightest, and most massive stars, the ones that live fast and die young. The O and B stars of Orion are gravitationally unbound, meaning they're not held together tightly like the stars in a globular cluster. Instead, they're more like siblings who grew up together but are now pursuing their own paths through the galaxy. This association includes not just the bright stars we can see with our eyes, but also many fainter stars and the molecular clouds where new stars continue to form. The entire Orion OB association contains thousands of stars spread across hundreds of light years. Betelgeuse, Rigel, Bellatrix, the Belt stars, the stars of the trapezium in the Orion Nebula, all are members of this extended stellar family. These stars are young by astronomical standards, mostly between 1 million and 10 million years old, compared to our Sun's age of 4.6 billion years. They represent the current generation of star formation in our region of the galaxy. 100 million years from now, most of these stars will have dispersed, drifting apart as they orbit the galactic center at different speeds. Some, like Betelgeuse and the belt stars, will have exploded as supernovae. Their remnants will enrich the interstellar medium with heavy elements, which will eventually be incorporated into the next generation of stars. This is the cycle of stellar life in our galaxy. Stars form in molecular clouds, live their appointed spans, whether 10 million years for the massive blue giants or 10 billion years for stars like our Sun, and then die, returning their material to space. The heavy elements created in stellar cores through fusion, and the even heavier elements created in supernova explosions, mix with the interstellar medium and seed the next generation of molecular clouds. Each generation of stars is slightly richer in heavy elements than the last. When the first stars formed in the universe, about 13 billion years ago, they consisted almost entirely of hydrogen and helium because those were the only elements created in the Big Bang. There was no carbon, no oxygen, no iron, none of the elements necessary for planets and life. Those elements were forged in stellar cores and scattered into space by dying stars. Every atom of carbon in your body was created inside a star. Every breath of oxygen was produced through stellar nucleosynthesis. We are, quite literally, made of star stuff. If you'd like to find Orion in your own sky, January is the perfect time. The constellation rises in the east during early evening and climbs highest in the southern sky around midnight. The three belt stars are your key to identification. Once you spot them, the rest of the constellation falls into place. Above the belt to the left, the reddish Betelgeuse marks one shoulder. Above the belt to the right, the blue-white Bellatrix marks the other shoulder. Below the belt, Safe and Rigel mark the feet, with Rigel being distinctly brighter. Hanging from the belt, you'll see the vertical line of the sword. The middle star will appear fuzzy through binoculars or a small telescope. You'll see why. That's the Orion Nebula, a stellar nursery 1,344 light-years away. If you have access to dark skies away from city lights, spend some time with the nebula. Even through modest instruments, it's breathtaking. For those in the northern hemisphere, Orion is best seen from December through March, with January offering the longest viewing time during convenient evening hours. For those in the southern hemisphere, Orion appears upside down compared to northern views, but it's equally spectacular and visible during the same months since it straddles the celestial equator. Here's a helpful tip: Orion can serve as a guide to other bright stars. If you follow the line of the belt stars to the upper right, you'll come to Aldebaran, the bright orange eye of Taurus the Bull, and continuing farther you'll reach the Pleiades star cluster. Follow the belt to the lower left and you'll find Sirius, the brightest star in Earth's night sky, part of the constellation Canis Major, the Great Dog. Orion is hunting, and his faithful dog follows him across the sky. As you observe Orion, consider the timescales involved. The light from Rigel left that star 863 years ago, during the height of the Middle Ages on Earth. The light from Almalam left 1,340 years ago, when the Islamic Golden Age was beginning. The light from Betelgeuse left 548 years ago, around the time of the Renaissance. We're not seeing these stars as they are now. We're seeing them as they were hundreds of years in the past. Betelgeuse might have already exploded as a supernova, and we wouldn't know for centuries until the light from that explosion reached us. This is one of the strange consequences of astronomy. We study the past because light takes time to travel, and the universe is so vast that even light, moving at its tremendous speed, becomes a slow messenger across cosmic distances. And on that note, we've completed our tour of Orion the Hunter, the brightest constellation in January's sky. We've examined the blazing blue supergiants of the belt, the massive red giant Betelgeuse approaching the end of its span, the luminous blue Rigel outshining everything around it. We've explored the Orion Nebula, a stellar nursery where stars are being born from clouds of gas and dust. We've considered the dark nebulae where cold molecular clouds hide the future sites of star formation. We've placed Orion in the context of our galaxy and the cycle of stellar birth, life, and death that has been running for billions of years and will continue for billions more. Thank you for joining me on this journey through one of the sky's most magnificent constellations. I hope you'll take the opportunity to step outside on a clear January evening, find those 3 bright belt stars, and spend some time getting to know Orion the Hunter. Until next time, keep looking up.